Today I will speak about the physics beyond standard model using the experiment NA62, that's an experiment located at CERN, in particular the SPS of CERN, and use a Kaon beam for all the physics. So, I already said is a high precision fixed target Kaon experiment. The main goal is to measure the branching ratio of the K plus going pi plus and 2 neutrino. Of course, then there is even a broader physics program that counts about lepton flavor violation, lepton number violation, count decay, and some hidden Saturn particle search. That, however, I will show something about some example of this broader physics program after the main goal that I will show just now. About the timeline of this experiment, it was approved in 2008. Then after some very fast pilot run and commission run in 2014 and 15, and the full detector installation in 2016, we had the first data set there in 2016. It was a very small data set. I will show that later respect to the other data set. But however, the first run of data taking, the complete run was from 2016 to 2018. Then data taking will be resumed in 2021 after some detector and beamline improvements that we are doing now, just now in this period. So what about this decay? Why is important? This decay is important because it's high sensitive to new physics, because it is a flavor change in neutral current process forbid at 311. You can see by this diagram that there are no one is at 3 level, and is suppressed by the CKM matrix. So it's very clean theoretically, and it's very easy to measure it theoretically, even because the hadronic matrix element can be extracted by the precision measurement of this decay, the K plus in pi0, positron and neutrino. So here you can see the standard model prediction. If you see, are precise at about 10%, okay? And then you can see the experimental result. Experimental result before NA62 is in particular by experiment. Here you can see the two articles, but however, A787, A989, and by Cot experiment, okay? And you can see that the experimental result have a precision that is worse respect to the standard model prediction. So the idea is to do an experiment with an issue that can reach the same precision of the standard model prediction, okay? So about new physics and this decay. This decay is very interesting, even new physics, and not only like to test the standard model, because the value of this, the branching ratio of the charge that you can see in on the x axis, and in the y axis there is the neutral decay instead. So the value of this decay can be predicted even inside the other model, not only standard model, but other new physics scenario, other new physics model, like for example, you can see here in green model with CKM like flavor structure, red model like custodian random syndrome, and then in blue model like Z prime with so not only Z but even Z prime, little x with T parity, and then there is other model like lepton flavor universality violation, leptoquark, minimal supersymmetry model. Here you can see many papers that speak about these other models, okay, and this decay. I loaded the presentation so you can find this link and search for these papers if you are interested about that. Let's see the state of art before NA62, and then with the NA62 run, first run. You can see from the plot on the left, there was many experiments interested in the chem physics, interested in this decay. So up to the early 2000s, no one experimenter reached the the measurement, to succeed to do a measurement, but just an upper limit. Then now you see the experiment in Brookhaven, the A787, and it is upgrade 8949. Succeed to do this measurement with this about 60%, 70% of uncertainty. Okay, here you can find even the articles. The NA62 with the first run succeed to collect a biggest amount of the proton charge, biggest amount of statistic of Kaon, so to improve even this measurement. That later, of course, I will show you the result of this measurement. First, let's speak about the detector. So all the detector that compose this experiment. The experiment use a primary beam of proton of 400 GeV coming from the SPS of CERN. Okay, the speed is about 3.5 seconds, and this primary beam hit a primary target, creating a secondary beam composed by pion, proton, and kaon. Kaon is just the 6%, but is what we are interested about. We're interested just in kaon, but it's just the 6% of the beam. The beam is 75 GeV, and we have to identify for the first thing the kaon, because we are not interested in the pion, proton. This can create some background. So indeed, in the beam line, we have like first thing the k-tag. K-tag is a differential Cherenkov that we use to identify the kaon and to give a time at the kaon, because it's very fast. It can give a time of about with less than 100 picosecond of resolution in timing, about 60. And then we have the GTK, that is the beam tracking. Is 3 station of silicon pixel. Is a very interesting tracker, because it succeeds to sustain a very high rate, because for example at the station 3 we have 750 megahertz of particle that hit the station, and it succeeds to measure it and track all them. Okay, then we have a system of veto, because we have to try to veto everything, because you saw that this decay is 10 to the minus 11, so we have to succeed to react all the other decay about the same amount, 10 to the minus 11. Okay, so we have a very big system to veto the photon. For example, the lab are large angle veto for photon. Okay, then we have a liquid krypton calorimeter, that is electromagnetic calorimeter, to veto photon here. So we veto photon from 50 milliradiant to 0 milliradiant, because we have even 2 small angle veto that are SAC and IRC. This veto, so photon even at 0 angle. Then we have a tracking system, STRO, that is a 4 chamber of with several straw, okay, to track, because we have even a bending magnet here, so we can measure even the momentum of the particle, the downstream particle. In this case, will be the pion for this decay. Because we have muon veto done by some hadronic calorimeter, MAV1, MAV2, and MAV3, that is a scintillator that use to veto the last muon, because there is a block of iron before that. Okay. Then we have the decay fiduciary volume that is about 60 meters. That is in this area, inside the lab. Then I show you fastly the result of 2016, 2017 that are already published. You can see the publication here and here. The 2016 was how you said before, was a fast data taking, and we get just one event in the region of the signal. Region of signal are here in red. You can see between 15 and 35 JV. And later, after this, I will show you why are divided in two. But where this is the peak of the pi plus pi 0, so the main background. And then in 2017, we found instead of 2 events. So with 2016, 2017, we succeeded to put just a limit with 90% of confidence level. With 2018, we succeed to improve a lot this measurement and succeed to arrive to get a real measurement of this decay, of this differentiation. And now we'll explain better the analysis of 2018. That is a bit the more complex because there was even a bigger statistic. So I will show you before the region interesting are two, region 1 and region 2. You can see here in the plot. In red is the histogram of the decay of our interest, the K plus in pi plus neutrino and neutrino, but is enhanced of factor 10 to the 10. Indeed, without this enhancement, you could not see that decay in this plot because it's too small respect to the background's decay. Okay, the background decay. Okay, I say you before. Here there is the peak of the pi plus pi 0, and this is the radiative tails. Then there is a K in mu neutrino, and this is still the radiative decay. There is the 3 pion decay, positive, and with the 3 charge, we can say, and that one with the 2 neutral pions. Okay, and there the decay with lepton and pion, this and this. Okay. For NA62, we used a different technique with respect to the experiment of Brookhaven, that is the decay on flat technique. So I showed before that we have a phylogenetic volume where the Kaons decay, and then we use the pion that are boosted. We use it this way with the boost, the Lorentz boost, because in this way we can react more easily respect to Brookhaven, the photon coming from the pi 0. So principle of this pi plus pi 0, that is a big background. Okay. Instead, Brookhaven used the decay on rest. So it was using the Kaon of a very low momentum that the decay almost at rest. So the signal, I already said, is very simple. It's done with 1 Kaon upstream, 1 pion downstream, and nothing else because the two neutrino are not detected. The signal region are these missing mass, and you said, two region in missing mass, and the momentum is improved with respect to the analysis of 2016-2017 because it's not anymore between 15 and 35 GeV, but it's between 15 and 45 GeV. So we improved the signal region, and so we improved the acceptance of our signal. The experiment, the part important for this experiment was the precise cinematic reconstruction. So reconstruct precisely mean the Kaon and the pion with the giga tracker, so the spectrometer upstream and the spectrometer downstream. To identify all the particles, it's important to identify the Kaon because it's the 6% of the just the 6% of the beam, how you already said, and to identify electron, muon, and pion because so we're interested only in pion, and we have to react all decay that have electron, muon, and then the detection of photons should be hermetic, detect all the events with a pi 0. It's important to have a timing under the nanosecond. Indeed, we have many detectors that can give timing about 100 picosecond of resolution, because in this way we have less problem of about accidental. So the pull-up of other events, other decay over the one that of our interesting. Okay. So with this, we succeed to have a reaction of muon of a bigger than 10 to the 7, a reaction of pi 0 bigger than 10 to the 7, and another 10 to the 4 of background suppression coming from cinematics, so coming off the selection of these two regions. Okay. Then in 2018, we divided the analysis in 7 different categories because depend of the Arden configuration of the momentum of the analysis. Because we did a bit different analysis with the momentum, and the configuration different because during the data taking we add a damper for the beam to reduce the sort of shield to reduce the amount of beam background that get inside the diffusion volume. Then we use some multivariate analysis for particle identification upstream background reaction. So here you can see again a plot with on the X the moment of the pion, on the Y the missing mass. Okay, so you can see in red the region of interest. We have the region of interest of that was used even on the old analysis, so between 15 and 35 GeV, region 1, region 2. And then we have an improvement of this region between 35 to 45 GeV that is used only in 2018 analysis. That you can see here a very big amount of background of K muon neutrino, a big amount of background of pi plus pi 0, okay, because this has the branch ratio just is a 0.2. The branch ratio of the mu neutrino is 0.6, so it's a factor 10 to the 11 bigger, about 10 to the 10 bigger than our decay of interest, so the pion and 2 neutrino. And then this is the area where there is mainly the 3 pion decay. Okay. And in the analysis, the selection for the pi nu neutrino is we select all the events with a kaon that decay. Then we search inside the fiduciary region. We select only particles with downstream that we identify like pion using the calorimeter and the reach that is a Cherenkov detector. Then we apply all the photon reaction of the muon reaction and all the multiple charge particle reaction to eliminate, to reduce the background of 3 pion. Okay. And this is what we get after the signal selection. The analysis was completely blind. So before the unblind that we did the last day, okay, live in a meeting of the collaboration, we cannot see what there is inside, how many events there is inside, okay? In blind analysis, it's important to not be biased, but from what you see inside the signal region. So you can see indeed what remain about the 3 pion background, the pi plus pi 0 background, and the muon neutrino background. Then we had some control region that we unblind before to unblind the signal region to see that to check that our analysis was correct, because we have a prevision about how many events to find in this background control region. If the prevision is correct, it's correct even the prevision of the background in the signal region. Okay. After that, I can show you the single event sensitivity. So this is important to understand how many events of signal we can find, considering the standard model value of the branch ratio. Okay. And this is obtained by the number of events that we found by using a control sample, that in this case the control sample is the pi plus pi 0, okay? Then we check for the trigger efficiency, the efficiency of the random veto. The random veto is all the events that are rejected, even if it could be good, due to the random veto of the veto detector. So for example, the photon reaction, and the multiplicity reaction, this reaction that can reject even the good event, because you open a window, you reject everything is around the signal of, for example, of a photon detector. Then there is, of course, consider the acceptance of the signal, acceptance of this control sample, and the branch ratio of in the standard model of our signal, the pi neutrino, and the 2 pion decay. Okay, so we had this single event sensitivity that we reached, so 10 to the minus 11, and these give us how many events that we can see in this analysis that I will show you later. Then we did the background estimation. I told you before, it is important to estimate the background that can find in the signal event and in the control region. So we can know about how many of the events that we will find in the signal region will be signal and many will be background. Okay. So the estimation is done in a similar way. We check for the events that are remaining in the region of the background. For example, for pi plus, pi 0, we check how many events remain here in this region, okay? And we multiply for a kinematical fraction. The kinematical fraction we obtain looking with a control sample, so it's not the same sample that we look for the analysis. It's a control sample. It's a sample unbiased, using a trigger unbiased, and we check the fraction between the pi plus pi 0 that go in the two region of signal and the pi plus pi 0 in the peak. So in this way, we do the estimation, this data-driven way, we do the estimation of the background that we can get in region 1 and region 2. The same procedure is used, for example, even for decay in mu neutrino and decay in 3-pion. For other background, we cannot use this data-driven estimation, but use the Monte Carlo, for example, the pi plus, pi minus positron neutrino. For that, we use the Monte Carlo, and we normalize what we obtain with the single event sensitivity. Another important background is the upstream background. I would say just the count are just the 6% of the beam, so we can have background coming from pion of the beam, or even decay of the Kaon in the beam. Okay, we can have so the background coming from decay of the Kaon before of the fiduciary volume, interaction of the Kaon with the spectrometer material, for example, and this can have in accidental a pull-up with a pion that go inside the spectrometer, the downstream spectrometer, especially if the real pion of the Kaon that decay go outside of acceptance of the detector. And this can be dangerous because we can fake a signal, because we can see a Kaon and a pion, but that pion is not associated really, is not from the decay of that Kaon. So it can mimic a signal of Kaon, pion, neutrino. To reduce this background, it's important the Kaon-pion association with the geometrical cut and the timing, a very fine timing between Kaon and pion, so about 100 picoseconds of resolution. Then we search for the geometrical region, and we use that even to the background validation and the estimation. And we use a data-driven background estimation, changes some cuts to check then how many of this background go inside. I said before, we have different sample. One difference between samples is the adding of this collimator. Okay, during the 2018 data taking, we add a collimator that can reduce the amount of background, because it's a very big collimator of our iron that make pass only events that are in the hole and block all the other pion coming from the bin line, and from pion coming from decay of Kaon before this collimator. Okay, this is the background summary. Okay, that we get from the estimation this way I told you, data driven, and someone with Monte Carlo. We estimate to get about, okay, this is an estimation, so 7.6, about 7.6 events of events, considering the Brinsky ratio of the standard model. Okay, and then instead we estimate to get about 5.3 event of background. And here are the validation of the background. We unblind the control region. So we get, for example, 0 in this control region. We was expecting 1.4. In this region was expecting about 11 events, and we get 8. Here we was expecting 32, we get 31. You see here we expected 7, we get 10. You see the estimation are always inside the 3 sigma by respect to what we get really unblind in that region. So we was really confident of our work and our analysis. And these are the control region, estimation control region for the dataset of pi plus pi minus a plus neutrino that was with Monte Carlo. Okay, estimation done with Monte Carlo. Even this way, you see that the estimation and the data are in a very good agreement, and the same for the upstream, the background, that are really in a good agreement. So this is before the unblinding, and after the unblinding we get 17 events observed over about 13 events expected. Okay. This is another way to show you the result, showing in a different missing mass. So integrating the result in the momentum. See, however, that there is a good agreement between the data and the expectation of Monte Carlo and data-driven method, both for background and for the main signal that we are looking. So the K plus in pi plus neutrino. And this is putting the plot with the different category I told you. So different momentum, different before and after the collimator, and 7 data instead are the data obtained in 2017 and 2016. So we put all together, where the biggest data set is however 2018. Okay, and in the end we get this result. That is 11 plus minus 4 plus 4 minus 3.5 about 10 to the times 10 to the minus 11 with 3.5 of sigma of significance. So you see that however we reached about a 30%, 35% of resolution of this measurement. That is a great improvement in respect to what was done by the experiment before. And then we have, of course, the next data taking that we start in 2021 to improve this measurement. This is a plot to show where we are now in respect to the past. So this was the measurement of 2017, and this is what we have now. And even the improvement of the theoretical expectation, even that did a very big improvement in these years. This is just a zoom of that. So for even till now, the standard model is inside, it's compatible with these measurements. Okay, so we don't have the standard model is still compatible, so we don't know if this measurement agree with the standard model completely or with some other new physics theory. But however, we are trying to improve the experiment to take more data to improve the precision of this decay. And then this is a bidimensional plot where we have on the Higgs the charged pion. So the charged decay are measured by the experiment in situ and measured by the refused experiment of Brookhaven. And then on the Y is the neutral decay with Koto exclusion for now, that is with 90% confidence is still here. And we hope that Koto will reach the standard model precision, so they can exclude and get a measurement near the standard model precision, so we can see even if this measurement is like compatible with the standard model or not. So we have the result of this analysis. This analysis of the completed run 1. We get so in total 20 events. Okay, expected background was 7. And this is I showed you before, the branching ratio is measured. It's compatible with the standard model with 1 standard deviation. And for the next run, we will do some improvement both in the bin line, in then detector, adding One station is the spectrometer to improve the precision of the momentum of decay, and to improve even the reaction of the upstream background. That was the main background up to now. And then we will have new calorimeter downstream, and we improve the dim and dump to suppress the count decay background the same way. Okay, now we start to see the broader physics problem in situ. So what we are looking even, especially for the beyond standard model, so new physics. Mainly we are looking for rare case decay, electron number evaluation, electron flight evaluation decay in Kaon, and some other exotic search, like every natural electron, dark photon, axion-like particle. And we show you just some example of this, because of course there is no time, because however there are paper in publication now. Let's start with electron flavor evaluation, electron number evaluation. Some example of these searches in NA62 are this decay, so K plus in pi minus and 2 positron, okay? K plus in pi electron and muon with many exchange of charge, so both the same charge or different charge, okay? And K plus in pi minus and 2 positive muon. This decay can be predicted in beyond standard model that use, for example, Majorana neutrino, that are, for example, in the diagram here on the right, where the Majorana neutrino can mediate this decay, and with model with inside the left quark that are more interesting now, especially after the measurement of the electron flavor universality evaluation done by LSCB. Okay, there's the anomaly that LSCB found, and now there is some more model looking at left of quark. And left of quark can explain even the decay of electron flavor evaluation if we count, of course. Here they are the previous experiment results by a BNL experiment by a previous experiment CERN in 848. You can here find the article. And NA62 wanted to prove these, there's estimation, there's upper limit. The main background are event with pion disidentification or pion that decay in flight, for example, in muon principally. For example, here I show you the plot, the result for K plus in pi minus and 2 positive muon. The expected background was less than 1 event, 0.91, and we get 1 event. Here in the middle is the signal region, that on the side is the control region. For the plot on the left, instead, we found the same analysis but done with the different charge, so with 1 negative muon and 1 positive muon. Indeed, you can find here that analysis agree perfectly with the peak of the K plus in pi plus, positive muon and negative muon. Okay, so you see that there's a perfect agreement between the Monte Carlo and the data, and here we found one event that is compatible with the expected background, and the current limit that we put with NA62 that you see is a factor about 2 respect to the previous upper limit. The same for the pi minus and 2 positron. We was expecting 0.16 event, okay, the blind region. We found 0, and this is the upper limit that we get. In the same way, with an improvement of about a factor 3 respect to the previous experiments. These are other 2 different decay, I would say, with a muon and an electron with the same charge of different charge. NA62 at the moment cannot do with the same charge of mu and electron with two negative charges because we use positive kaon. But however, we can do this one and the one with different charge. This and the opposite. The prediction of the ground was one event, and we observed at 0 in this case. In this case, the prediction was 0.92, and we observed 2 events. So we're comfortable with the background estimation. Here is a resume of the limit that we observed for now, and with the improvement of factor 2 and 3 for the first two, factor 12 for the third, and factor 8 for the fourth. Okay, for the first two, we used only the 17 data that we know that is very small with respect to the 18 data sample, so we can improve even that. And then we have other 3 decay that we are studying, but still we are not competitive with the previous decay experiment, or however, we are still in the studying, in the analysis. So stay tuned, because in the future we'll get even this result, and we'll publish this paper. The first 2 papers are already published. Here are the link. That is the same paper from that case. Another example of this exotic search is the heavy neutral lepton. So NA62 is looking even for the heavy neutral lepton. That is one model of neutrino minimal standard model theory that accounts the oscillation of neutrino and the mass of neutrino. So is improving the standard model theory that don't count the neutrino with mass, don't count of about the oscillation. So this new theory can be an explanation even for dark matter, even of baryogenesis. And for this theory, there are 3 heavy neutral leptons, one with the mass about 10 keV, and 2 with the mass around the JV, okay? The one with mass around JV can be observed both in production, both in decay. Here in the plot on the right, you can see the exclusion for now. They are interested of the first mass, the one around 10 keV, okay? And in the histogram down, the histogram below, you can see the area in green that is interested by NCGO for the search of the other 2 heavy neutral lepton, okay? In red is the exclusion due to the computation of the baryogenesis, so the Big Bang nucleosynthesis. This is the exclusion due to the baryon asymmetry in the universe, and the exclusion due to the Suso mechanism. The branch ratio of the decay of particle in the lepton, heavy neutral lepton, that in this case the particle is kaon, okay, kaon lepton, heavy neutral lepton, can be obtained, can be estimated using the normal standard model decay in a normal neutrino times a kinematic factor that enhance the value of this branch ratio even up to a factor 10 to the 5, and then a matrix element due of the changing of the lepton with this other the neutrino with this heavy neutral lepton. Here is show you the test sample that we have for the positron case. So the kaon in positron and heavy neutral lepton, we have a sample of 10 to the 12 of K plus, the K in the fiduciary boson, and for the muon case, just 10 to the 9. Here on the left, you can find what we get. So what is the background of the event that go in K electron, heavy neutral electron. The background is mainly due to OK in muon neutrino with a muon that decay in electron, and then background coming from the pion that decay, pion from the Beyoind that decay in electron and muon. Okay, this background create even this small change in the slope of the background, of the total background, that can create some problem in the analysis, and it was reduced this change of slope using even a different analysis just in this small part that reduce the acceptance and the sensitivity of this analysis. And later I will show you the effect that have this change analysis. And then this is the peak of the K plus in in the positive neutrino, but these, however, don't give a big background because the region area of the signal where we're looking for the signal is between these two arrows. And we're looking at the signal, looking for a spike, a peak in this continuous spectrum. Because every peak, every spike can be a signal of heavy neutral electron production. The same way for the K plus in positive muon and neutrino, we're looking in this region, and the background is due to K in muon neutrino and some radiative decay, so with that of some photon. And a very small background is due to 3 pion, where 2 pion are lost and 1 pion decay in muon. So here are the acceptance respect to the possible mass of this heavy neutral electron. In red is the acceptance of the electron with this auxiliary value here. That is the other analysis that is done just in the area near this change of slope that I showed you before, because we are looking, we look for a peak, and to look for peak, we use the bandwidth, the side band around where we look for the peak to compute the background under the peak. Okay, so here can give a problem, this change of slope for the background estimation. So we use this auxiliary selection that's just a difference of cut momentum, about 20 JV instead of 30 of the electron, to reduce this slope, just that. This auxiliary, however, change the, how you see in this way, change the sensitivity respect to the mass in this area, because we have less acceptance, so we have even a smaller sensitivity. And then for the same acceptance and sensitivity for the muon decay. Here you can see the result. This is the upper limit that we get for the electron decay and for the muon decay. For the electron decay, we have a small spike that go about 3.6 of lack of significance, so away from the estimated background, but accounted with the effect of look elsewhere, sorry, the significance go to 2.2. This effect is just the fact that you're looking in all this mass range, so it's bigger the probability to find a peak for a fluctuation as a statistic, just a statistical effect. However, accounted that the significance go to 2.2. And here are the summary of what we observed, looking at the even at what get by the other experiments. So you can see in blue what is get by with decay of Kaons and muon, okay, from a first run of NA62 in 2007 with the very old detectors. Then was improved with the data taking of 2015 of NA62, and then we get here the muon. instead for the experiment A949, and the preliminary in black of NA62. That is, here have the same sensitivity, but here was a standard that was improved the sensitivity got before by NA2 of the other experiments. In blue here is this part excluded already. I will show you at the starting by the Big Bang nucleosynthesis. It was the same here in red, okay? Is here in blue for muon, and this is red, the same part already excluded by the baryon nucleosynthesis for the electron. And for the electron, so NC0 excluded about all this part. So up to about 383 MeV, 383 MeV, the is excluded for the electron. Okay, instead is excluded for muon. So here opposite. So here for the is for muon, this is here for electron. Okay, sorry. Oh yes, is for electron is excluded about 300 MeV, 340, and for muon is excluded here less 300. But then there is an improvement that we can get with NA62, because this is just 2017 with 2018 data. Like for the electron, we can reach probably the same exclusion of the electrons. Then, for the last example, we have an example of important rare Kaon decay. Decay plus, impi plus, mu plus, mu minus, and then another important decay that with decay plus, impi plus, electron and positron. So why these two decay are important? They are important especially after the B anomaly seen by LSCB. The B anomaly was a possible evidence of lepton favoring universality violation, and these two decay are really similar of what LSCB used. LSCB used B, the decay in Kaon with 2 electron, 2 muon, and as you can use Kaon that go in pion and 2 electron, 2 muon. So this is important to test the lepton favoring universality with some decay that are similar to what used the LSCB. These are favor change in neutral current decay similar to like the plus to neutrino, and are described with the chiral theory, okay? The chiral flavor theory, using the exchange of one virtual photon. These are the preliminary results of NA62 with the K plus impi plus muon. The result used about 10 to the 12 Kaon, using the data sample of 2017-2018 that are the biggest data sample. And for now, the results are consistent with the K impi plus and 2 electron measured up to now by the other experiments. Now in this institute, not up to now a measurement of the K plus minus because they were not obtained by the trigger, but we are in plan to improve the measurement of the K plus and 2 muon with 2021 data, 21, 22, 23, and to get even the measurement of the 2 electron version. This is the branch radiation measured up to now that, however, is one of the best results of the measurement of this decay. Here are the previous articles. The article of NA62 is not still done, but in the future we'll go out with an article, a paper about this decay. So in conclusion, for decay plus impi plus neutron, that is the most important decay of this experiment. We did an analysis of the completed run 1. Is compatible for now with the standard model prediction inside one standard deviation. The branch ratio is about 11 to 10 to the minus 11. Okay. is the most precise measurement obtained of this differentiation so far. Instead, for the other decay, for the broader physics problem, we have improved the upper limit for the lepton flavor evaluation, lepton number evaluation channels. We improved the limit of the matrix element for the even natural lepton, and we have a preliminary result for K in pion muon and positive muon consistent with the K pion and 2 electron for the parameter of important for the lepton flavor universality evaluation. Then other analyses are ongoing, and other results will be obtained in the future.